There were two ways to build a hydrogen bomb. America found the first one, the Teller-Ulam design: radiation, compression. X-rays compressed the fusion fuel before the explosion dispersed it. The Soviets tried the second Sloyka layer cake, alternating layers of fission and fusion materials. Simple but limited. RDS-6 was built this way. It yielded 400 kg. Powerful but not a true hydrogen bomb. Sakharov found the third idea, similar to Teller-Ulam but different, suitable for Soviet engineering, suitable for mass production. RDS-37 was the product of this third idea, 1.5 megatons, but the design was scalable, with the same principle. 10 megatons, 50 megatons, 100 megatons could be built. 6 years later, the Soviets detonated the Tsar Bomba, 50 megatons. History's largest explosion, RDS-37, was the first step on that road. This is the story of how Soviet scientists solved the hydrogen bomb puzzle their own way, how they matched American achievement through independent innovation, and how one design opened the door to unlimited destructive power. The hydrogen bomb was born in America. In November 1952, the United States detonated Ivy Mike in the Pacific, 10.5 megatons, the first thermonuclear explosion in history. The device used the Teller-Ulam design, a fission bomb. The primary released X-rays that compressed a separate container of fusion fuel. The secondary, the compression created the extreme density and temperature needed for fusion. This was a revolutionary concept. It meant there was no theoretical limit to the power of a nuclear weapon. By adding more stages, each compressing the next, yields could be increased indefinitely. But Ivy Mike was not a weapon. It was a building-sized apparatus. It weighed 62 tons. The fusion fuel was liquid deuterium, requiring massive cryogenic cooling systems. The Americans had proven that thermonuclear fusion could be achieved, but they had not yet created a deliverable weapon. The Soviets were watching. They knew they were behind, and they were determined to catch up. Soviet nuclear scientists took a different path. They did not know the details of the Teller-Ulam design. American secrecy was effective. The Soviets had to develop their own solution. The lead physicist was Andrei Sakharov. He was young, brilliant, and driven. At age 29, he was already one of the most important scientists in the Soviet program. Sakharov developed what he called the Sloyka design. The name meant layer cake in Russian. It described the structure of the device. The Sloyka used alternating layers of fission and fusion materials. The fission core was surrounded by a layer of lithium deuteride, the fusion fuel. This was surrounded by another layer of fission material, usually uranium-238. When the central fission bomb exploded, it compressed and heated the fusion layer. Some fusion occurred, releasing neutrons. These neutrons caused the outer uranium layer to fission as well, adding more energy. This was a boosted fission weapon, or a hybrid design. It achieved significant yields, but it was not a true hydrogen bomb. The fusion reactions contributed to the explosion, but they were not the primary source of energy. RDS-6, tested in August 1953, used this design. It yielded 400 kg, 10 times more powerful than Hiroshima, but nowhere near the megaton range of Ivy Mike. The Soviets had achieved something, but they knew it was not enough. The layer cake had fundamental limitations. The design could not be scaled indefinitely. Adding more layers did not proportionally increase the yield. The physics simply did not work that way. In a Sloyka device, the fusion fuel was compressed by the direct pressure of the fission explosion. This compression was relatively inefficient. Only a fraction of the fusion fuel actually underwent fusion. To get higher yields, you would need more fission material. But there were practical limits to how much fission material could be assembled, and the weight would become prohibitive. The Americans had solved this with the Teller-Ulam breakthrough. By using radiation implosion rather than hydrodynamic pressure, they could achieve much higher compression ratios. This made fusion ignition more efficient and allowed for much higher yields. The Soviets recognized this limitation. They studied the data from American tests. They analyzed the yields and the fallout patterns. They tried to deduce how the Americans had achieved such enormous power. Sakharov and his colleagues knew they needed a new approach. The layer cake was a dead end for megaton-class weapons. Something else was required. The race was on to find the third idea. The breakthrough came in 1954. Sakharov and his colleague Yakov Zeldovich developed what they called the third idea. Was their version of radiation implosion. The concept was similar to Teller-Ulam but arrived at independently. Instead of relying on the direct physical pressure of the fission explosion, they would use the radiation itself. When a fission bomb explodes, it releases enormous amounts of energy, as these X-rays travel at the speed of light, much faster than the expanding physical debris. If properly channeled, they could compress a separate mass of fusion fuel before the explosion dispersed. The key insight was that the primary and secondary stages needed to be physically separated but connected by a radiation channel. The X-rays from the primary would fill this channel, creating uniform pressure around the secondary. This pressure would compress the fusion fuel to the extreme densities needed for ignition. Sakharov called this concept radiation implosion. The Americans called it radiation coupling. The physics was the same. With this breakthrough, the Soviets could finally build true thermonuclear weapons, weapons that could match and exceed American designs, weapons with no theoretical upper limit on yield. RDS-37 would be the first test of the third idea. The design work for RDS-37 began in early 1950-5. The device used a new radiation implosion principle. A fission primary would generate the X. These would compress a secondary stage containing lithium deuteride, the solid fusion fuel. Using lithium deuteride instead of liquid deuterium was crucial. Liquid deuterium required massive cooling systems. Lithium deuteride was a solid at normal temperatures. This made the weapon practical and deliverable. When neutrons from the primary struck lithium-6, they produced tritium. The tritium then fused with deuterium, releasing enormous energy. This was the same fusion reaction that powers the Sun. The secondary also contained a uranium-238 tamper. The fast neutrons from fusion would cause this uranium to fission as well, adding to the yield. This is why hydrogen bombs are actually fission-fusion devices. The engineers at Artemis-16 worked around the clock. They had to solve countless technical problems. How to shape the radiation channel, how to time the implosion perfectly, how to contain the forces until fusion ignited. By autumn, RDS-37 was ready. It weighed about 3 tons. It could be carried by the Tu-16 bomber. It was a true weapon, not a laboratory experiment. The test was scheduled for November. Semipalatinsk was the Soviet Union's primary nuclear test site, located in northeastern Kazakhstan. It covered an area of 18,000 square kilometers. Since 1949, it had been the proving ground for Soviet nuclear weapons. Dozens of tests had already been conducted there. The site was remote but not uninhabited. Villages dotted the surrounding steppe. Farmers and herders lived within range of the test effects. The Soviet authorities did not evacuate them for most tests. For RDS-37, special preparations were made. The expected yield was unprecedented, 1 to 2 megatons. This was far larger than anything previously tested at Semipalatinsk observation. Bunkers were constructed at various distances. Instruments were deployed to measure the explosion's effects. Aircraft were prepared to collect samples from the mushroom cloud. The test was codenamed Test Number 37. It would be the 37th nuclear test at the site, but it would be unlike any that came before. Weather conditions on November 22nd were poor. Heavy clouds covered the test area. Visibility was limited. Some scientists recommended postponement, but the political pressure was intense. Moscow wanted results. The test would proceed as scheduled. November 22nd, 1955, 9:25 in the morning. Local time. The Tu-16 bomber approached the target at an altitude of 12,000 meters. In its bomb bay was RDS-37, suspended from its release mechanism. The crew was tense. They knew they were carrying something unprecedented. Their aircraft had been specially modified to carry the 3-ton weapon. They had trained for months. At the designated coordinates, the bomb was released. A parachute deployed, slowing its descent. This would give the aircraft time to escape the blast zone. RDS-37 descended through the cloud layer at an altitude of approximately 1,800 meters. The detonation mechanism triggered. The primary fission bomb exploded first. In an instant, it generated X-rays of incredible intensity. These X-rays, traveling at the speed of light, filled the radiation channel surrounding the secondary. The secondary stage was compressed by radiation pressure from all directions simultaneously. The lithium deuteride was squeezed to enormous density. Temperatures soared to hundreds of millions of degrees. fusion-ignited. Deuterium and tritium nuclei slammed together, fusing into helium and releasing neutrons and energy. The reaction cascaded through the fuel. Fast neutrons caused the uranium tamper to fission, adding more energy. The total yield was 1.6 megatons, more than 100 times Hiroshima. The third idea had worked. Asterisk. The fireball expanded to 3 kilometers in diameter. It was visible from 300 kilometers away despite the heavy cloud cover. The flash temporarily blinded observers who looked directly at it, even through protective goggles. The mushroom cloud rose to an altitude of over 15 kilometers, penetrating deep into the stratosphere. It spread across the sky, its top illuminated by the sun above the clouds. The shockwave was devastating. Within the designated test zone, structures were obliterated. Bunkers designed to withstand nuclear explosions were damaged. Instruments were destroyed, but the effects extended far beyond the test zone. 50 kilometers from ground zero, in a village called Karol, buildings collapsed. The shockwave, reflected and amplified by the temperature inversion in the cloud layer, hit with unexpected force. Windows shattered, walls cracked, roofs caved in. People were injured by falling debris. A 3-year-old girl named Monya died when her house collapsed. She was the first confirmed civilian casualty of a Soviet thermonuclear test. The Soviet authorities suppressed this information. The death was not recorded in official statistics. The family was warned to remain silent. The incident remained hidden for decades. Asterisk. The scientists were jubilant and horrified. RDS-37 had proven that the third idea worked. The Soviet Union now possessed true thermonuclear weapons. The gap with America had been closed, but the unexpected casualties cast a shadow over the achievement. Sakharov and his colleagues had not anticipated the effects of the weather conditions. The temperature inversion had channeled the shock wave in unpredictable ways. The test demonstrated both the power and the unpredictability of thermonuclear weapons. Even with extensive planning, the effects could not be fully controlled. The forces unleashed were beyond human management. Sakharov was deeply affected. In his memoirs, written decades later, he described his growing unease with the weapons he had helped create. The death of the child weighed on his conscience, but in 1955, there was no time for reflection. The arms race demanded more weapons, bigger yields, better delivery systems. Sakharov and his team were already working on the next generation. RDS-37 was just the beginning. The design could be scaled up. Much larger yields were possible. The Soviets would prove this 6 years later. Asterisk. RDS-37 was not just a single test. It was a proof of concept. The third idea could be applied to weapons of any size. The same physics that produced 1.6 megatons could produce much more. The only limits were engineering constraints and the willingness to build such devices. Over the following years, Soviet designers created increasingly powerful weapons, each built on the principles proven by RDS-37. In 1961, they tested the Tsar Bomba 50 megatons, the largest nuclear explosion in history. It was based on the same radiation implosion concept, scaled up to the extreme. The original Tsar Bomba design was capable of 100 megatons. The Soviets reduced it to 54, the test to limit fallout. Even at half power, it was 3,300 times more powerful than Hiroshima. All of this traced back to RDS-37, the third idea, the breakthrough that gave the Soviet Union true thermonuclear capability. The arms race accelerated. Both superpowers built arsenals of thousands of thermonuclear weapons. Each warhead was based on the same fundamental principles proven in the 1950s. By the 1960s, humanity possessed the power to destroy civilization many times over. RDS-37 was one of the steps that led to that capability. Asterisk. What happened to the people behind RDS-37? Andrei Sakharov became a hero of the Soviet Union. He was awarded the Stalin Prize 3 times. He received every honor the state could bestow. He was wealthy by Soviet standards, privileged beyond most citizens' dreams, but the experience changed him. The death of the girl at Karol haunted him. The testing programs killed others as well. Soldiers exposed to radiation, civilians downwind of test sites. The human cost of nuclear weapons was becoming clear. In the 1960s, Sakharov began to advocate for nuclear test bans. He supported the Partial Test Ban Treaty of 1963. He started speaking out on human rights and political reform. The Soviet government turned against him. The man who had given them the hydrogen bomb became a dissident. He was stripped of his privileges. He was exiled to the closed city of Gorky in 1980, forbidden from contacting foreigners. In 1975, Sakharov was awarded the Nobel Peace Prize. He was not allowed to travel to receive it. His wife accepted on his behalf. After Gorbachev came to power, Sakharov was released from exile. He became a member of the Soviet parliament. He continued to advocate for reform until his death in December 1980-9. The father of the Soviet hydrogen bomb died as a peace activist. The man who created the third idea spent his final decades trying to limit the weapons he had made possible. RDS 37 was a turning point in human history. It proved that the Soviet Union could match American thermonuclear capability. It closed the gap in the arms race. It made the Cold War nuclear standoff truly mutual. But more than that, it demonstrated that the secrets of thermonuclear weapons could be independently discovered. The Soviets did not copy the American design. They created their own. This meant that other nations could do the same. Today, 9 countries possess nuclear weapons. Several have thermonuclear capability. The physics is the same everywhere. The third idea, or its equivalent, underlies them all. November 22, 1955, a bomber over Kazakhstan. A weapon dropped through clouds. A flash that lit the steppe. 1.5 megatons, 100 Hiroshima, 1 dead child, 1 scientist who would become a dissident. The third idea changed everything. It gave humanity the power of the sun, the power to create and the power to destroy. We still live in the world that our DS-37 created. The weapons are still there. The ideas are still known. The danger is still real. The third idea cannot be unlearned. It can only be controlled. Whether we are capable of that control remains the question of our age.